This case is about conducting medical insurance pricing using machine learning model. First, let's have a look on the case background. Correctly priced medical insurance is crucial for ensuring access to affordable healthcare while maintaining the financial sustainability of insurance. Underpricing and overpricing will both have financial losses for different parties involved. And a well-balanced pricing strategy helps ensure that premiums can reflect the true risks and cost of care, enable broad participation, fair risk sharing, and the provision of essential medical services. And the objective of this case is to develop a best machine learning regressor model to correctly price medical insurance. And the model should minimize the MSE on the test data set. First, we should import some necessary libraries for data handling, visualization, and various machine learning functions. And let's have a look at our data set. The variables are age, sex, BMI, children, smoker, region, and charges. And among them, the charges is the target variable that represents pricing of medical insurance. Next, we conduct data setup and data splitting. We first change smoker and region into numerical type, and we also split the dataset into feature matrix X, which contains age, sex, BMI, children, smoker, region for training the machine learning model, and target variable Y, which is the charges, and it is the variable that the model needs to predict. And we also split the dataset into 80% training set and 20% test set, and to ensure the model is evaluated on unseen data to prevent overfitting, and the model is also good for generalization. And since the data is all set, we can try on different regression models to evaluate their performance. And from the code shown in the left picture, we try linear regression, lasso, ridge, elastic net, and random forest model with and without RFE and with different parameters. We set the RFE function to select the top 3 features that is most important to the target variable charges and change different default parameters inside each model. And after several attempts, we discovered that the best model is the random forest model with RFE and random state equals to 68. And we plot the learning curve of the random forest model we choose. The learning curve for random forest regressor shows how the training and validation errors change with different training set size. And according to the learning curve shown in the right picture, we can see that the training error, which is MSE, is low and stable, which indicates that the model fits the training data very well. While the validation error remains consistently high and does not decrease significantly as the training set size gets larger, which suggests that the model does not generalize that well to unseen data. And we also train the MLP regressor model, but the MLP regressor model does not perform better than the previous random forest model we choose. And now we can confirm that random forest model is the best performer among those regression models. And next, we can try to adjust some of its hyperparameters to find out whether it can have better performance. We perform hyperparameter tuning for a random forest regressor using grid search CV function to find the best model that minimizes MSE. We first standardize the features to normalize the data to zero mean and unit variance for comparison. And we also train and evaluate a baseline model with default parameters for further adjustments. And we also define hyperparameter grid for optimization. The N estimator controls the number of trees in the forest. Max depth limits the depth of trees, while deeper trees capture more complexity but may overfit. And the minimum sample split controls how many samples are needed to split the node, while higher values of this parameter prevents overfitting. And the minimum sample leaf is the minimum number of samples per leaf node, while higher values of this parameter force the model to generalize more. And then we perform hyperparameter tuning using grid search CV function to search exhaustively over all parameter combinations. The CV equals to 5 means we conduct a 5-fold cross-validation, which ensures model performance is robust. And also scoring equals to negative mean squared error. We use negative MSE to find the best model. And from the output, we can see that the model with the minimum validation MSE has the parameters of maximum depth equals to 10, minimum sample leaf equals to 4, minimum sample split equals to 10, and estimators equals to 200. However, after we plot the learning curve of the random forest model we chose, we can find that though the new random forest model performed well in the training data set with a small MSE, it performs even worse on the test data set after adjusting these parameters. Therefore, we still choose the simpler random forest model with RFE and random state equals to 68 to be the best performer on the test data set. And this is the final regression model we select, and the performance is shown on the right picture. And that's all for our case study.